Hello, students. This is the third integration practice video. We are working integrals 15 through 20. Well, we begin with 15. Okay, sometimes when we have one function divided by another, it is substitution. If we try that here, if we let u be the denominator, du would be 3x squared minus 2x dx. Now you notice that the numerator is not a multiple of 3x squared minus 2x. And so substitution is probably not the best approach here. However, we see polynomial divided by polynomial. The degree of the numerator is less than the degree of the denominator. And so this will be partial fractions. This is also a definite integral, and so we will need fundamental theorem of calculus. Let us begin by rewriting. Step 1, we factor the denominator. This is not too bad. We have x squared, x minus 1. Okay, now we have to remember the general form of the partial fractions decomposition. Okay, we have one distinct linear, so we will have a over x minus 1. But then this x squared is a repeated linear term. So we will have plus b over x plus c over x squared. Now, we see the common denominator. It's staring at us over here on the left-hand side. Maybe I'll give a little more space, and I could just show what I'll multiply each term by. Then we can move to the next line. The first term, I would multiply by x squared over x squared. The second term, I would multiply by x minus 1, divided by x minus 1. And then the third term, I would just multiply by x minus 1, divided by x minus 1. Okay, now this will help me. So in the next step, we have x squared plus 3, and this will equal ax squared plus, and looking here, we have bx squared minus bx, and then plus, we have c, x minus c. So I'm going to regroup things. We have x squared times something plus x times something, and then plus our constant. We have x squared times a plus b. We have x times c minus b. And then the constant is minus c. This yields a plus b is 1. This yields c minus b is 0. And this yields minus c is 3. What I did is I equated the coefficient in front of x squared with the coefficient in front of x squared. There's a 1 here. The coefficient in front of x with the coefficient in front of x, which is 0 on the left-hand side, and the constant with the constant. Now, there is very little work to solve this linear system. The bottom one says c is -3, and then the second line says that b equals c, so b is also -3. And then the first line, we have a will be, let's see, 1 minus b, which is the same thing as 4. I'm ready to write my definite integral. We go from 2 to 3 of 4 over x minus 1 minus 3 over x minus 3 over x squared. All right, we have 4 ln absolute value x minus 1 minus 3 ln absolute value of x, and then we will have minus 3, we add a power, divide by the higher power. This is definite, and so we evaluate between 2 and 3. 2 and 3. Next line. First, we evaluate at the upper limit of integration. You notice I will have 4ln2 minus 3ln3. And then this is really plus 3 divided by 3, which is 1. Okay, subtract off, evaluate at the lower limit of integration. We have 4ln1 minus 3ln2. And then plus, this will be 3 over 2. Well, we can combine some things. First of all, natural log of 1 is 0. So I'm left with 7ln2 minus 3ln3. And then I have plus 1 minus 3/2. So minus a half. Wonderful. I want to point to the directions on 16, 17, and 18. We are instructed to complete the square. Okay, so maybe I will complete the square underneath in black. We have x squared plus 4x, and then we can move the 20 over here. Now, in order to complete the square, we look at this. We take half of this number and square it. So that would be 2 squared, which is 4. So I put this here, and then at the same time, I can subtract it here. I'm really thinking about grouping this part and this part. Very nice. Underlined in green highlighter, this is x plus 2 squared. And then this is plus 16. So I'm ready to integrate. We have an integral, 1 over x plus 2 squared plus 16 dx. This is a tan inverse. So we have 1 over 4 tan inverse of x plus 2 over 4 plus c. This is a great question. We move on to 17. Once again, we can look at the denominator and complete the square. So here we have x squared plus 4x plus 5. We take this number, half of it, and square it. Just as in the one above, we have plus 4. And then we subtract 4 over here. And we group. Let's see. This one is blue highlighter. This one is green highlighter. Okay, I'm left with x plus 2 squared plus 1. Well, let's go back to my integral. The question is, what do I do now? Because I have x minus 2 in my numerator. Well, let's see. If we think about this as substitution, and we let u be the denominator, note that I could have thought about this before completing the square as well. Well, du would be 2x plus 2 dx, also known as 2x plus 4. And I don't exactly have that in my numerator. If I did, or if I had a multiple of that in my numerator, I wouldn't have needed to complete the square. But what I will do is write x minus 2 as x plus 2, plus something, constant. And then I can write this integral as a sum of 2 terms. Let's do this on this side. Note that x minus 2 is x plus 2 minus 4. Okay, so this integral is, it's an integral x plus 2 over this denominator dx minus the integral of 4. I will do my work for substitution over here. Only the first term. We have u as x plus 2 squared plus 1. du is 2x plus 2 dx. in my integral, I have x plus 2 dx, which is 1/2 du. We have an integral, 1 over u times 1/2 du minus this one. We can go ahead and integrate. We have 4 tan inverse x plus 2. Now we have a half ln absolute value of u. This part I've already integrated. I can just copy from the line above and paste. And finally, we just go back to x on the first term. And here is the final answer, where I went back to variable x in the first term. I also dropped the absolute values because what's inside the logarithm is always positive. Now, we are going to do one more where we complete the square, but one comment that I wanted to make here, quite often, if we stare at something like this, our first instinct is not complete the square. Our first instinct would be, well, set up a partial fractions decomposition. But if you look at this quadratic in the denominator, the discriminant, which we know is 4 squared minus 4 times 5. So that's 16 minus 20. That is negative. So this is an irreducible quadratic, meaning, well, this is as simple as it gets. You cannot make that any simpler through a partial fractions decomposition. And similarly for this one. So completing the square certainly came in a hint, or in the directions, I should say, but it is also the best approach for 16 and 17. Okay, 18. This is our last one where we are directed to complete the square. What I'm going to first do is work with x squared minus 6x plus 8. You notice what's underneath the radical is negative, this quadratic. So we move this over. We take half of minus 6, which is minus 3. So we take plus 9 minus 9. We underline. This one gets green. This one gets blue. This one is x minus 3 squared. We have minus 1. Therefore, my integral is the integral 1 over square root. Now we have negative this quadratic underneath the radical. So this will be 1 minus x minus 3 squared dx. Maybe I should do a recollection here. I might erase it after we write it down. We haven't used this integral in our integration practice at all yet. We integrate 1 over square root, let's say 1 minus t squared dt. This is the sine inverse. This would be sine inverse of t plus c. All right, so using this, you notice we have the sine inverse of x minus 3 plus c. Always lovely to think about the sine inverse. 19. We are given the integral from a to b of f of x dx is capital M. We have part A, part B, part C, where we are evaluating some other definite integrals in terms of M. Well, A, I think of as the simplest in the group. This would just be a to b f of x dx plus the integral a to b of 8 dx. So part A, we have capital M plus 8 b minus a. Letter B, we have substitution. In fact, we will also have this in C. This exercise really forces us to change our limits of integration, which is why I like it. So if you let u be x minus 3, then du is dx. Very nice. But now we change our limits of integration. Maybe I should make this black for my side work. So when x equals a plus 3, u is a. And when x equals b plus 3, u is, well, b plus 3 minus 3, which is b. Okay, all of this is my side work for substitution. So letter B, you notice we write it as an integral of u. U ranges from a to b. We have f of u du. Well, this is exactly capital M. Very nice. Letter C. Once again, we have to think substitution here, change our limits of integration. So in this case, u is 2x. du is 2 dx. We have dx, which is 1/2 du. Let's change our limits of integration. My x ranges from a over 2 to b over 2. Here u would be a, here u would be b. Okay, we have an integral from a to b, f of u times 1 over 2 du. This is 1/2 the integral a to b, f of u du. You see my final answer, we have 1/2 times capital M. This is the last question, and I consider this to be intricate, without a doubt, but it's good for us. Now, let's talk about this question before we get started. So we are handed a derivative, w prime. We are also told w of 2. Then we want to find w. So first, we will be integrating this function. Then we need to use this to solve for the constant c. Our final answer will not have a plus c in it. Okay, so in order to address this, okay, the integral tan inverse of y over 2 divided by 4 plus y squared dy. How can we think about this function? Well, I see a tan inverse. I also see 1 over 4 plus y squared. In my mind, when I think of the tan inverse of x, I think of its derivative being 1 over 1 plus x squared. So this suggests substitution where we use tan inverse of y over 2 as our u. Maybe before I jump into that, which I will do most of the work on the next page, let us just calculate the derivative of tan inverse of y over 2. I'm going to simplify this. So first we can think chain rule. We have 1 over 1 plus y over 2 squared. That's derivative of the outside, evaluated at the inside, and then we multiply by the derivative of the inside function. Okay, I can simplify this here by multiplying by 4 divided by 4. So we have 4 divided by 4 plus, well, this term is y squared over 4. If you multiply that by 4, we have y squared. And finally, we get 2 over 4 plus y squared. Okay, so this is some side work. Now, let's move to the next page and work on this integral. We need the space here. All right, so as I mentioned, we will let u be the tan inverse of y over 2. Okay, now, du. I'm just coming back here, copy, paste. We calculated this. Handed to me in my integral is 1 over 4 plus y squared dy, which is just divide by 2, so 1/2 du. Okay, here is my side box. We have an integral. Well, this is not too bad. It's just u times 1/2 du. We integrate 1/2 u squared over 2 plus c. Now we can write wy equals 1 over 4 is going to be tan inverse y over 2 squared plus c. So if I didn't have this, I'd be finished with the question. But now I need to use that w of 2 equals pi and solve for my constant. So we set pi here, and then we have 1 over 4 tan inverse of 1 squared plus c. What is the tan inverse of 1? Well, it says that the tangent is 1 and the angle is between minus pi over 2 and pi over 2. Tangent of what says sine and cosine are equal. That will be here along the line y equals x. So this happens at pi over 4. So let's evaluate. Have pi over 4 squared. And now you can see my constant c is pi minus, here we have pi squared 6 over 16 times 4, which is pi squared over 64. My goodness. You see, I mentioned this would be a bit intricate, although none of the steps are too bad. So, final answer, maybe I will do this in black. W of y is 1 over 4 tan inverse y over 2 squared plus pi minus pi squared over 64. Well, isn't this a function for you? Very nice. We went out with a bang on this question 20. Okay, well, this is the end of the third video of our integration practice, and I hope this whole playlist was helpful for you. Thanks so much.